So today, we're introducing what we call electromagnetic induction. Electromagnetic induction. And in this area, we are going to see how EMF can be induced whenever we have a changing magnetic flux. And we expect to see some two important laws that govern this field. And those two laws are what we call the Faraday's law and the Lenz's law, as we shall see. Now, whenever a magnetic flux changes in a conductor or in a circuit, an EMF ends up being induced. The result, whenever the magnetic flux threading the conductor or the circuit has changed, brings about an induction. The EMF that is induced and depends on two items. One, the changing magnetic flux with time. Then the other one is the changing magnetic flux acting in a way that it opposes the change that is causing it. In that sense, we shall be describing the two laws when you talk about those two items. The rate of the changing magnetic flux and also the acting of the changing magnetic flux in a sense that it opposes the change that causes it. All those bring about an induction EMF. And with that, the changing magnetic flux may be due to the relative motion between the flux and the circuit or the conductor, or it may be due to the flux being produced by an alternating current, which is by nature of varying both the direction and the magnitude of the current. So, with those few remarks, we have some illustrations which we can use to predict or to show us how some of these items do work. For example, if you have a coil like this one here, and this coil you thread it through a magnet, this magnet, as you thread it through to and fro, you will induce an EMF within the solenoid and the current will be detected to be flowing. I have some video which I will show you which has that idea, and the current can be detected using either a deflection galvanometer or a voltmeter. Then also some of the applications of these items of electromagnets include what we call the Malgaev trains. The Malgaev trains are what people normally call, it's maglev. People call them normally the electric trains. Now these trains, there was an image I had displayed here of a train. There is one which looks like that. This train is actually suspended in air. And the suspension comes as a result of the different, it has around 4 magnets that are designed on it. So you can see this part here. The train is above here. So this is a magnet right there and a magnet right there. And different magnets are put in different corners of the box of the train. And they can be put at different polarities, North Pole, South Pole, and the like. And whenever there is a move, because the train is moving, when it is moving, it is going to change the flux of the magnets. And whenever it changes the flux of the magnets, it is already suspended by the magnets because the like poles repel and like poles attract. So as it is being repelled away, at the same time, it's being attracted back. So when it moves, it has a changing magnetic flux that is being induced, which brings about an EMF that makes the train move. So it is called a maglev train, reason coming from the definition of what we call the magnetic letivation trains. And that's why they are called maglev trains. They originate from magnetism. So magnetism is a very important aspect, and this aspect can be seen by what we call electromagnetic induction. So very many images, very many definitions will come up as a result of electromagnetic induction. And we shall see that very many items can be produced because of this knowledge or field of physics, which is called the electromagnetic induction. So as you can see that kind of train, how it is designed. So you can see according to this image, it is suspended. But because of the magnets which are here, yeah? And those magnets are arranged in such an order, like if you see this image, yeah, where is my image? It is here. If you look at this image, that is the order of arrangement of the box of the magnet, of the train. So each cabin you have has 4 magnets in it, whereby the polarity of the north, when it meets the north, it is repelled away. When it meets the south, it is what? Attracted back. But because it is moving, it generates a changing magnetic field within the aligned magnets on the rails and in the box of the train. So it's a very important aspect that we can see from that definition. Another illustration we can talk about here is there was an illustration other than a train, because in Uganda these trains have not yet arrived, but I think Kenya now has one, even Tanzania has one. We are supposed to have one because I remember they commissioned them at the same time, but our country still has that problem of delay. So we are still delaying the commission and even starting the construction of such a train. So if you look at also this other image, it is also displaying the same. But there was another image I wanted us to look at. Okay, so these are the other kinds of images you can see for the trains. But I've showed you how they work using the concept of magnetism. Now we are going to see coils being wound. And whenever coils are being wound, and we have a changing magnetic flux, due to the flux linking different coils, we shall be inducing an EMF, as we shall see in the different definitions that are going to come up. Those of you who have bypassed Seka Market, as you climb towards Equatorial Mall, there are shops there which are always wound, which are always counting coils. We always give numbers of magnetism. We say a coil of 1,000 tons, of 2,000 tons. So there are guys who always be there and just count number of tons on a given coil, because they build coils from there. There are some mega technicians who are good at building coils from down there. So they can build for you a coil, which can be for a pump, to pump water. They can build for you a coil which can be to generate electricity. So depending on what you want. But all that, they are going to use the concept of what we call electromagnetic induction. So electromagnetic induction is a wide field of study, and it has brought about so many changes in life of electricity. And it is from here also that we advance the knowledge of alternating current circuits. If you look at this one, for example, you see this image is demonstrating Faraday's law. There is already a field inside the solenoid. Now, when you thrust through a magnet, which is the north pole, the deflection on the voltmeter takes the same direction as motion of the north pole. When you pull away the magnet, because when you pull away the magnet, you're going to change the flux. When you push in the magnet, still you're changing the flux. So whenever the flux inside there changes, it leads to an induction of an EMF. And that is what Faraday's law states. It states that the magnitude of the induced EMF is directly proportional to the rate of change of the flux linkage, or the flux linking the circuit, or flux linking the solenoid, according to this image. So we are going to see more of these illustrations and how they come about. So you can visit the internet, you see very many different people talking about these laws and how best they can be applied in our day-to-day activities. But like I've said, very many images, very many fields of physics can be used to have this knowledge of physics, which is electromagnetic induction. I don't know whether you've seen bicycles with headlamps. Those of us who have seen those bicycles with headlamps, they used to have a device called the dynamo. A dynamo is a device. Let me see if I can find one here. A dynamo is a device which dynamo. It's a device which can be used to generate electricity, but in a way that it has a rotating coil. That rotating coil is attached to a bicycle. Very good. My image is here. So this image is what I want us to see. I don't know that you can see this image of this bicycle here, where we have the bottle dynamo. There is an image here, and this image you see right here. The dynamo is this part. So it has a rod which is attached to a round item which is running over the tire. So this tire moves this round piece, because the round piece is attached to the coil like this. So whenever this one spins and rotates, even the rod does what? Rotates. So the rod rotates, and within here there is a magnetic field. So the rod rotates within a magnetic field, and whenever it rotates within a magnetic field, it's going to induce and what? An EMF. We also have alternators. They also play a very good role in inducing EMF. It's just that we can't have this image. Okay. Another item is here. Motors can be built using this same knowledge. I already mentioned that. These kinds of motors, if you take a look at them, we just see them, but some people don't know the physics behind. So you as physicists, you should know that when you see those coils inside there, even vehicles, even motorcycles, they all have these kinds of motors. The car has a motor which, when running, it induces an EMF which charges the battery of the car. Otherwise, the battery of the car will always wear out. But whenever the car runs, the motor runs and it induces an EMF which is connected to a changing magnetic field, and then it will induce an EMF. And in that sense, the battery keeps on charging all the time. So that's why the car can never lose battery, unless if the battery is faulty. But the battery has to be always recharged whenever the car is in use. So some motors are built to do that. Other motors, you'll see them from the different definitions you have around. For example, also we can see this. We also have electricity that can be generated. You've heard of electricity generated from wind, yeah? It's because this windmill, when it rotates, it spins, and it has a rod connected to it, and that rod goes to a motor where we have an electric field, a magnetic field. So whenever the rod changes, which is within a magnetic field, it will induce an EMF. So we shall have some wind generators produced. So we have wind generators, we have hydro generators, we have, this is now a water pump. I have one like this one, I think, at my farm. Then you have generators, this one in yellow. Have you seen people who start generators? The local simple generators, leave alone the generators you have in schools which need switches. Those are alternating ones, direct, but there are those DC generators which when you first pull, you've seen that cable they pull? The cable they pull it because the cable is connected to a wheel. That wheel rotates within a given magnetic field inside the motor of the generator. And then it produces what? An EMF, which is electricity. Which electricity is direct current. And now that direct current can be converted to AC using a device that can be connected to the system. And whenever you have AC systems, they can also be in position to use such generators. So, as you can see, this is also a wind generated EMF as a result of the different motors. All these generators, we've seen them in town. Yeah, you've seen such shapes of generators. So they are all using this concept of electromagnetic induction. So all those devices, they induce EMF, they induce current, they induce electricity. Why? One, as a result of motion. What is moving? You need to find out what is moving. Is it a coil? Is it a rod? Is it the whole circuit or the whole system moving within a given magnetic field? If yes, then with that condition, you can be in position to predict how the magnetic field is playing a role in inducing an EMF. So with that, we can now go back and talk about our laws. And the first law is what we call, I've sent you the notes, you'll have them. So we have laws of electromagnetic induction. And the first law is what we call the Faraday's law. the Faraday's law. And this Faraday's law, it states that the magnitude of the induced EMF, the magnitude of induced EMF is directly proportional to the rate of change of flux linkage. The flux leaking either the coil or leaking the circuit. Now, in this case, EMF is directly proportional to the change in flux. Flux is represented by psi, by phi, by that symbol phi. So with that, the total flux is N phi, whereby that psi represents the flux of a single coil. So if the coils are N, then the total flux is N psi. So the rate of change of flux is directly proportional to the EMF that can be induced. Then we have the second law, which is the Lenz's law. Lenz's law. It states that the EMF induced is in such a way that or is in such a direction that it opposes the change causing it. I want to go back to the other man who was pushing the magnet in and out. So other definitions, we shall meet them in the notes. Let me first go back to this gentleman. There's a gentleman who was pushing in and out the magnet. I wanted to show you something about it. I've been positioned to see it again. What does that mean? It means that when the magnet is being pushed inside, for example, a solenoid, yeah, you will see that one, the EMF induced is going to be in this form. Okay, let me do an illustration. The EMF going to be induced is going to be in this form. That if you bring a magnet which has a north pole and south pole, and you have a coil, when you bring this magnet closer, as you push it closer, the coil is going to design a field whose magnetism is going to appear as if it's a north pole this way and as if it's a south pole on the other side. So that when this magnet approaches, it is going to be experiencing a repulsion. Now, when you try to pull away the magnet, this is what is going to happen. As you try to pull away the magnet, it will, if the magnet is still, this is south, this is north, the induction will be in a form that this side is going to create a south pole as this one creates a north pole. In a state that when the magnet is being pushed to the solenoid tries to oppose the change that is causing it. So the change that is bringing about the magnetic induction in the solenoid is acting in a way that it opposes what is causing that magnetic induction in the solenoid. So if the north pole is trying to make sure that the solenoid becomes magnetized, then the solenoid will act in a way that it will bring a polarity which opposes the magnet approaching it. Whereas when you move away the magnet, still the magnetic field will change. So when you draw away the magnet from the solenoid, the magnetic field is going to change in a state that it will create a south pole at the exit. And this south pole at the exit is trying to attract back the north pole that is going away. So that is what the Lenz's law states. It states that the induced EMF is going to always act in such a way that it will oppose the change that has caused it, right? So with that, we can look at also this equation, which says that EMF now is going to be equal to a negative K dN psi dt. So this negativity is what talks about the opposition of the change that has caused the EMF, or that has caused the magnetic field that has changed. So with that, the negative sign satisfies Lenz's law. The negative sign satisfies Lenz's law. And K is a positive constant of proportionality. If the flux is measured in Webers, the flux is measured in Webers, time in seconds, and then EMF in volts, then 1 volt is equal to K times 1 Weber divided by 1 second. So the SI units of K become volts. You'll see that if K is, because now if you look at K, we are saying K is a constant. So if K is a constant, then if you have 1 volt and 1 Weber, then K is going to be equal to 1. That is, if you have 1 volt and you have a flux linkage of 1 Weber in a time of 1 second. Just like we derived the equation for force is mass times acceleration. And we assumed a force of 1 Newton, a mass of 1 kilogram, and an acceleration of 1 meter per second squared. Then the value of the constant of proportionality from Newton's second law was confirmed to be 1. So even here, the value of the constant K is 1. And with that, it means that the EMF induced is always given by a negative dN psi dt as our mathematical expression for the EMF that has been induced as a result of a changing magnetic flux. And this equation is what they call the Faraday-Newman's equation. This is Faraday-Newman's equation. So with that Faraday-Newman's equation, we can be tasked now to get or to find or to describe an experiment to prove the following what? Laws. And the first experiment is going to be for proving Lenz's law. Now, because I've already sent you the write-up, we are going to pass through this experiment very fast. And according to what I've already sent, we have the images. Let me share the screen. So we have the experiment set up as shown. So with this experiment set up as shown, initially, the first circuit you see, we set up a battery with a resistor and with a deflection meter from side A to side B. And then from that, if you connect a battery which is having a positive terminal and a negative terminal, current flows from the positive. So the deflection on the meter, as you see, is from A to B. So that one can help us get a reference deflection, which shows you the side or the direction of deflection when a battery has been connected to the circuit. Then for the second one is right here. The second one is when you connect there a solenoid, and then you move a magnet of known polarity. The magnet, when it approaches the solenoid, it will induce a north pole. But the north pole induced, the direction of the north pole on the solenoid is the direction where current starts flowing from. So current starts from the north of the solenoid. If your solenoid is like this, and your solenoid has this as the north pole and this as the south pole, then the direction of flow of current is going to be in this direction. If you have a system you've created here, and this is maybe your magnet with the north pole and south pole. So the polarity in the solenoid is such that the north polarity of the magnet induces a north pole at the same position, so as it opposes the incoming magnet. Now, if the current flows from the direction of the north pole in the solenoid, then if current flows in the same direction, you see that the deflection has been maintained to be going in this other same direction like it was before. Now, what happens when we pull away the magnet? When we pull away the magnet, remember I told you, we end up inducing a south pole. Because the EMF induced in the solenoid now is trying to act in a way that it opposes the going away of the magnet. That is why it induces a polarity of south, which south is trying to attract back the magnet. And in that sense, it will induce a north on this other side, and current will now be flowing from this side. Hence, the deflection now changes direction to that side. Here it was going this way, even here it was going that way. So those three images are showing you how the deflections are realized. And with that, that will be verifying what we call Lenz's law. So for the write-up, you'll go through that write-up I've sent, but the explanations do not differ from what I've just said, unless if someone has a question on this verification. So if no question on this verification, they can also ask you to explain how Lenz's law can be an example of the principle of conservation of energy. Now, when you look at the next page on the write-up that I sent you, that definition is right there, which is right here. So this is explaining how Lenz's law is an example of the principle of conservation of energy. So if you have a galvanometer, which is detecting the deflection, and we have our solenoid like we had it before in the illustration, and we thrust through a magnet. The thrust of the magnet, as the magnet approaches the solenoid, we induce a north pole, which is trying to oppose the incoming polarity of the magnet. And if it does so, current starts flowing from the north pole, and the deflection galvanometer will deflect in the direction where the current is going. Now, if you consider a north pole of a permanent magnet that is thrust towards one end of a coil connected to a moving coil galvanometer, the induced current flows in such a direction as to create a repulsive force. Remember, I told you the solenoid will induce a polarity, which polarity is going to bring about a repulsion force, trying to oppose the incoming what? Permanent magnet. So the repulsion force on the magnet has been experienced. Now, the agent or the person who is moving the magnet must provide mechanical energy to overcome that force. Now, you are trying to push the magnet to the solenoid, but the solenoid is trying to repel away the magnet. So what do? You increase the energy. So you put in more energy to push this magnet into the what? Into the solenoid. So you are providing mechanical energy. So when you provide mechanical energy to overcome the force, the work done in overcoming the repulsive force provides the electrical energy of the current in the coil. So this energy is dissipated as heat in the coil, hence mechanical energy provided by the external agent. The external agent, I'm assuming you, the person pushing the magnet. The mechanical energy provided by the external agent to move the magnet towards the coil becomes the electrical energy developed in the coil by the current. So the magnet coil system loses the mechanical energy as electrical energy is growing. So if this electrical energy is growing as a result of loss in mechanical energy, then we can say we have conserved the mechanical energy. And with that, we can say the Lenz's law can be used to explain the principle of conservation of mechanical energy. It is a very common question which they ask for people to explain how Lenz's law can be used as a principle of conservation of mechanical energy. And please be always in position to handle that and do such explanations. Unless if someone has a question before I go for the experiment to verify Faraday's law. Do you have any questions? So if no questions, You can go ahead and also verify Faraday's law. So, to verify Faraday's law, the experiment is set up as shown. I remember I've told you there are some examples of induction devices that are connected with moving rods or wheels. So this one here is made up of a system which has a permanent bar magnet. The permanent bar magnet is this rod you see here. This is the permanent bar magnet. Then it has a rotating wheel this side. The wheel is being rotated. Okay. So an example, even the generators I told you, they have a rotating wheel. When the person pulls that generator wheel with a string, that wheel, the moment it rotates, it picks up an EMF as a result of the change in the magnetic flux it induces. When you put it, that's why they put it so hard. When they put it so hard, if you put it slow, it won't change so much. So the induction will be low. But when you put it so hard, the induction will be high. So it can easily bring about a high EMF, which high EMF will make the wheel have an EMF that keeps on rotating it over with time. And the more it rotates, the more EMF it will induce. Hence, at the end of the day, the generator will keep on running again and again. Now, with the system shown as above, this is a rod I've showed you for a permanent magnet. So there is a polarity here of the North Pole. Okay, so there is field lines, or there is magnetic field that is running. So these arrows are showing you magnetic flux that is coming from that bar magnet. We have here a rheostat, and then we have a galvanometer, and then we can get to predict the direction of motion of current. Now we have brushes, which brushes are the contacts, and those contacts are at X here and at Y there. Those are our contact brushes. And with that, the copper rod AC is made to rotate, because we told you we have a wheel which is rotating it by means of a wheel around the North Pole of a long magnet. If I can proceed, someone is in the chat. Teacher, pardon, you were breaking. Lucy, what pardon did you miss?
Teacher, when you're explaining how it rotates, before what you've just explained right now, the previous.
Mechanical energy conservation.
Yes.
Yeah. Kakati, now I was saying that if you're to go back and look at I was saying they can ask you to explain how Lenz's law is an example of principle of conservation of energy. Okay. And I was saying that if you thrust a magnet, I think Lucy, you understood how the opposition comes in. That when you thrust a polarity of a magnet, which is North Pole, the closed side of the solenoid will induce which kind of polarity? Lucy?
The same
polarity. Yes, not so. And if it's the same polarity, why does it induce the same polarity? According to what I've explained before. It induces the same polarity so as to oppose, so as to oppose the change that is causing it.
Yes.
So as to oppose the coming in of the magnet, not so. All right? You understand that, okay? Lucy, are you still together?
Yes, teacher.
Now, because of that repulsion force this magnet is experiencing from the induced polarity in the solenoid, you who was pushing, I'm assuming, let me assume, my glass here is the solenoid. This is the magnet I was thrusting in. As I was thrusting in the magnet, the open part of the solenoid here is now opposing my magnet. Now, if my magnet is being opposed to move away, me who is thrusting it, me the agent who is pushing it, I use a lot of mechanical energy to push it in. Okay? Lucy, are we still together?
Yes, teacher.
Now that energy I bring in to push this magnet inside by force, it is going to overcome the repulsion force which had been induced by the polarity in the solenoid. Are we still together? Yes?
Yes, teacher.
Now, that work we do in overcoming that repulsion force, yeah, provides the electrical energy of the current in the coil. So that work you're doing, the energy you use to do that work is converted into electrical energy in the coil. So this energy is dissipated also as heat in the coil, hence the mechanical energy provided by the external agent to move the magnet towards the coil becomes what we call the electrical energy. And with that, all the electrical energy developed in the coil by the current. So with that, the magnet coil system loses mechanical energy as it gains electrical energy. So with that, remember there is a principle of conservation of energy. We never lose energy or we never destroy it, but we convert it from one form to another. So the more you do work, which is mechanical energy, to push in the magnet, the more you are going to create electrical energy. So the energy becomes conserved. That the energy you have used to push in the magnet is going to be converted into electrical energy. Is that better?
Yes, teacher. Thank you.
Okay, welcome. So it is from there that we have said now we can introduce Thingy's theorem, Faraday's law. And we can also experiment and confirm what Faraday's law states. I've already talked about the illustration. So having seen the illustration, we can proceed and have the write-up. And we say a copper rod, which was named AC, is made to rotate by means of a wheel. Remember, I told you there is a wheel which will rotate to make the rod rotate. The rod is connected to a galvanometer in series with a variable resistor via the brushing contacts XY. The wheel is then turned at a constant speed so as to cut the rod across the field of magnetic flux B. Let me take you back there. Now, according to this illustration, we rotate the coil, the rod. As we rotate the rod, it is going to rotate within this field. There is a field here. There is a field here. Okay? And now we are rotating this. So as we are rotating it by this wheel, it is going to rotate through a given field. And whenever we rotate it through a given field, we shall induce an what? An EMF. So what does it say further? So with that, the wheel is turned at a constant speed so that the rod cuts across the field. The galvanometer is observed to give a steady deflection, indicating that the steady current is flowing in the circuit. Keeping the circuit resistance constant, the rate at which the wheel is turned is varied. For each rate, the time of completion of a revolution is noted. So every time you turn the wheel and you make a complete revolution, you note the time of revolution. And every time you do that, also you note the rate at which the wheel has been turned. You can now get to know the different EMF that has been induced. And by that, the corresponding deflection on the galvanometer also can be noted. And a graph of deflection against rate of rotation is drawn, and this gives a straight line through the origin, whereby the rate of deflection is directly proportional to the rate of rotation. So the more deflections you get, they result from the rate at which you are rotating the wheel. So the more you rotate the wheel, the more you shall get a deflection on the galvanometer. Hence, the EMF is directly proportional to the deflection and is directly proportional to the rate of flux cutting through the given field. And with that, we have proved or we have confirmed what Faraday's law actually states. Now, with that, there is another way also we can induce an EMF using what we call a turning coil. Sometimes people say a search coil. And with that, you can go to this next illustration of the work I've sent, which will be predicting that definition. Before that, this is how it looks like. So EMF induced by a turning coil. You connect the coil to a galvanometer, and that coil is in a wound form. Then what you do, you thrust a bar magnet close to it, then the coil can rotate through 90 degrees. As you see, this arrow is showing you that the coil is going to rotate through 90 degrees, which arrow is right here. So the coil is going to turn as it goes on the right-hand side, and we expect it to turn through 90 degrees as a result of the magnet being brought close to the coil. So with that, when you turn to the right up, this is what it talks about. A narrow coil, which is a such coil, is connected to a galvanometer and arranged such that its plane is perpendicular to the bar magnet. It is then uniformly turned through 90 degrees. That is plane. That is its plane is parallel to the bar magnet now, and the magnetic flux linkage then changes from maximum to 0, and the induced EMF causes the galvanometer to give a deflection. Now, whenever this coil is going to turn and it's going to rotate, remember it comes as we have EMF induced as a result of changing flux or moving items in a given changing magnetic field, or moving conductors or rods through a given field. So at this stage, we have made the coil rotate. So we have made it move. When you make it move, you end up making it bring about a deflection in the galvanometer. So the rate of rotation and deflection of the galvanometer are noted as a reciprocal of time and current respectively. Then the procedure is repeated for several values of t, and the corresponding current values I are recorded. Then a graph of I against 1/t is plotted, and with that graph, we can be in position to obtain a straight line which will confirm or which will predict the variation of current induced with the reciprocal of the time of rotation, which is going to be directly proportional because of the straight line. And with that still, it will show that it is confirming what it predicts to be Faraday's law. So in general, we have some experiments that show that magnitude of induced EMF increases with 1. Magnitude of induced EMF can increase with 1, the rate of change of the flux linkage. Now, the rate at which the flux linkage can change depends on the speed of rotation, whether of the bar, of the rod, of the coil, whatever you are rotating, or increasing the relative velocity between the flux and the coil. Then the second one, it can also depend on the cross-sectional area. What area are you sweeping? What area are you moving? 3, it can depend on the number of turns of the coil. The coil you have is of how many turns? 1,000, 500, 1,000, 2,000, 10,000. The number of turns of the coil matter. Then lastly, it also depends on the strength of the magnetic field of the magnet producing the flux. So the strength of that field matters to predict the size of the EMF that has been induced. And with that, we can talk about that in a mathematical form and say the EMF that has been induced depends on 1, we have said the number of turns. 2, we have said the cross-section area. 3, we have said the magnetic flux density. And 4, we have said the rate of rotation or the speed of rotation, which is the angular velocity. So the EMF induced depends on nab, omega. Now, it is from there that we can go ahead and also introduce what we call the magnetic flux. So the next definition is going to be called magnetic flux. Psi. So if you have field of flux density B, and you have a coil that is passing through, or that is allowing a field to pass through it, and the coil is slit at a given angle, theta, whereby the normal to the coil makes an angle theta with the field, and the coil or the disc, as you can see it there, is at it's having an area small a. Then with that, if you have this as your field, and this is a disc, which is going to be rotated through the flux of magnetic flux density B. Then you have a normal to this disk, which is making an angle theta. And this disk has an area capital A. So we can imagine you can either have a disk or we can have a coil. A coil of area capital A whose normal makes an angle theta with the magnetic field of flux density B. The flux through the coil phi is defined as the product of the area of the surface and the component of the magnetic flux density that is normal to the surface. So if one wants to get the magnetic flux phi, the magnetic flux phi is going to be given by the area that you're threading through the field times the component of the magnetic flux resolved normal to the coil. So it means you're going to move this magnetic flux normal to the coil by compressing the angle theta. So along this line, it would be B cos theta. Now, when it is normal to the coil and you multiply by the entire area of the coil, then you'll get the total flux that is leaking that coil or that is passing through that coil. So the total flux is got from AB cos theta. And this gives the number of magnetic flux lines piercing normally through a given area of a surface. So when they ask you to define what is magnetic flux, magnetic flux as a definition is the number of magnetic flux lines piercing normally, or magnetic field lines piercing normally through a given area of a surface. Yeah, so we have seen this, I think, earlier before, but now it is coming back a little in electromagnetic induction. Hence, for magnetic flux density, also you can say it's the number of magnetic flux lines piercing normally through 1 meter square or 1 square meter area of a surface. So you make B the subject and still define. You can now define magnetic flux density in terms of magnetic flux lines. So it can become A cos theta. So that's why we are saying one can also define magnetic flux density as the number of magnetic flux lines piercing normally through 1 square meter area of a surface. Then from there, we induce another definition, which we shall call the magnetic flux linkage. Now, that is flux for only 1 turn of the coil. Now, if the coil has very many turns, then we get what we call magnetic flux linkage. Magnetic flux linkage, which is going to be N phi, which is the total flux due to the total number of turns you have. So if that was only 1 turn in the beginning, now we have N turns. So if a coil has more than 1 turn, say N turns, then we can say its magnetic flux linkage is the sum of the magnetic fluxes linking a coil by the individual turns of the entire coil. So the coil has very many turns. But now I'm saying that if you want to get the flux linkage, you look at a coil that has got more than 1 turn, and that 1 turn more than 1 turn implies that it has around N turns. So its magnetic flux linkage is the sum of the magnetic fluxes linking the coil by the individual turns of the coil. So it is called magnetic flux linkage of the coil, and it is given by the following equation. Remember, we had already seen that flux phi is given by what? A, B cos of theta, where B is the flux density, A is the cross-section area of the coil, then theta is the angle of inclination of the coil, and it is the angle between the normal and the magnetic flux density, the normal of the coil. Now, total flux, which is magnetic flux linkage, is N phi, which can also be got from nab cosine of theta. So we should be seeing and knowing very well how all these equations are being brought about. So even if you visit the internet and you find such equations, you should know that this is talking about magnetic flux linkage or total flux. So it can be defined as the sum of all fluxes of the individual turns of the coil. So magnetic flux linkage. In summary, we can say is the sum of all the fluxes of the individual turns of the coil. So, and this expression is right here. So whenever they ask you for magnetic flux linkage, we shall use that equation. Now, with that definition, we can go to Faraday-Newman's equation. Remember, I had showed you earlier the Faraday-Newman's equation as this. Let me take you back to that equation. What is it? It is here. Remember the Faraday-Newman's equation? You see that equation? That is what we call the Faraday-Newman's what? Equation. So from the Faraday-Newman's equation, you see there is an aspect where we have flux linkage. So you can go and substitute the flux linkage, and I trust all of you are very good at differentiation. So the return of mathematics and the return of tree is today. So from there, we can see that E is equal to a negative d dt of n phi. But n phi is the total magnetic flux linkage, remember. And we have seen that n phi is actually equal to nab cos theta. So with this, we shall have E is equal to a negative d dt of nab cos theta. But theta is omega t. Okay? So if you want to differentiate, you can finally now deduce that E is equal to a negative d dt of nab cos omega t. So if you go back to thingy, those of us who have, I think some of you have covered AC circuits. If you have covered alternating current circuits, then you can see that some of these items are mentioned. And when you differentiate this, you'll end up inducing a sine omega t for the voltage, which is a positivity. So that's why some of the voltage becomes V is equal to V naught sine omega t because of the change in the flux. So what if I defined it as the product of magnetic flux and the number of turns of the coil? We have so many variations and options of definitions. So it's better you pick one which you feel is appropriate, okay, rather than in case maybe you're forming up your own. Now, with that, we can also get the definition of what we call a Weber. But before I can take you to a Weber, if someone is to go ahead and differentiate this is what you get. You will get a negative N, A, B, then you get a negative sine of omega t with omega. So this gives us nab omega sine omega t. Now, because this is sinusoidal, it is in form of trig functions, and the trig function there is sine, then it can be defined as EMF is equal to E naught sine omega t, where the value of E naught is what shall call the peak voltage, peak to peak voltage. I think when I speak some of those things, you understand. So the peak to peak voltage E naught is equal to nab omega. Okay, so with that essence, you'll be in position to predict whatever you want. Now, if you want to get the definition of the Weber, the definition of the Weber also can be asked in physics. And this is the magnetic flux linkage of a circuit if the induced EMF is 1 volt when a flux is reduced uniformly to 0 in 1 second. How can we come to that? Remember, I had showed you earlier. Let me rub off this part a little.
Teacher, before you rub off, it said, where has that omega come from? The second one.
Okay. You know how to differentiate trig functions?
Yes. Oh.
We use PTA. You know PTA? Eh? When you're differentiating a trig function, for example, cosine of n of m theta, you first differentiate the power and you get n cos of n minus 1 of m theta. Then you differentiate the angle and you get what? M. Then you differentiate the trig function. When you differentiate cos, you get a negative sine of the same angle. Then the answer becomes n, a negative m sine of m theta cos of n minus 1 of m theta. Now, if it is in figure form, to see it clearly, if you have cosine of 5, power 5 of 3 theta, the answer will become 5 cos of 4 3 theta times power, trig function, differentiate cos, you get a negative sine of 3 theta, differentiate the angle, you get 3. So you get a negative 15 sine 3 theta cos of 3 theta power 4. Now here, if you have a constant like what we differentiated, we have differentiated the cos omega t. The power is 1. You'll have 1 cos power 0 of omega t times a negative sine of omega t, the trig function, then differentiate the angle, you get omega. Because this is power 0, any number power 0 is 1, you get a negative omega sine omega t. So that's how, madam, the negativity omega, the omega came in. Okay?
Yes, teacher. Thank you.
So if you go back to our now, if you want to define the definition of a Weber, you consider EMF induced to be 1 volt in 1 second, and then you can make n phi the subject, because n phi is the SI unit, is the Weber, is the magnetic flux linkage, whose SI unit are Webers. So if I want to get a Weber, what do? I do this. You'll have EMF induced is equal to change in flux linkage with change in time. So if I get a change in if I have the change in time as 1 and I have 1 volt induced, so 1 volt will be equal to total flux linkage out of 1 second. So it is from here that n phi, remember n phi is measured in Webers, which will have now 1 Weber up here. So 1 Weber will be equal to 1 volt times 1 second. So that's why we are saying the definition is the magnetic flux linkage of a circuit. The Weber is the magnetic flux linkage of a circuit if the induced EMF is 1 volt when a flux is reduced uniformly to 0 in 1 second. So the change in flux becomes the original flux you have, minus 0, because the change in flux is from what you have before to 0 over the change in time, which is in 1 second. So you are changing the flux from what you had to 0 in 1 second. When you do that, the flux, the magnetic flux linkage required to do that is what we call 1 Weber. So let me finalize with these special cases just to talk about them. You can go and read about them so that next time when we describe their derivations and computations, because we are going to look at one item at a time. For example, a moving rod, and we look at the EMF induced. EMF, when a moving charge, look at the EMF induced. When a moving disk, look at the EMF induced, and so on and so forth. So according to that, you see it shows special cases, and the special cases we want to talk about in this area will be the following. Among them, you'll meet what we call EMF induced in a moving rod or in a moving straight conductor. And that EMF induced is always given by this expression. E is equal to BLV, where L is the length of the conductor, and then V is the velocity with which the rod is moving, and then B is the magnetic field in which it will move. If it moves at, this is perpendicular now to the field. If it moves at an angle to the field, you will have BLV sine of theta. Then secondly, EMF induced in a rotating coil. In a rotating coil, we have derived it earlier. I derived it, it's what I talked about and made the derivation. As you can see, that EMF is given by the following equation. E is equal to omega n, omega nab sine of theta, and I showed you how it came about. Even a colleague had just asked how I had differentiated to come to that. So we shall do those derivations again and how those equations come about. So all these equations, we are going to derive them because they are examinable. So we shall be covering one, we can either cover one per day or two. If we land on a short one, then we can cover 3, but we can't cover all of them in the next lesson. I doubt if we can do that because we have some examples to consider as well. Then we also have EMF induced in a moving charge. A moving charge is the same as that one of a moving rod, which is BLV. The length of travel of the charge, the velocity at which the charge travels, then the magnetic field in which it is moving. Then we also have EMF induced in a rotating disk. In a rotating disk, as you can see, it will be given by the cross-sectional area times the magnetic flux density times the frequency of rotation of the disk, which is the same as pi r squared BF. So that will be the EMF induced in a rotating disk. So we shall have to derive all of them. So please, if you can, go read about them, and you come when you're not so green, as I'll be speaking. They are inductions. So are the SI units for magnetic flux the same as those of magnetic flux linkage? No. Magnetic flux linkage are Webers. Then magnetic field, or magnetic flux density is what? Tesla. Remember? So they are different. So this is the magnetic flux linkage. The other one is B, which you're talking about. Okay, with that, I just got my Johnson & Johnson jab, so I'm feeling a little bit exhausted. Allow me to stop here. Unless if someone has another question. Yes, please. Wow, your network is squeaking. Can you type? Hello? Is he typing? Found some book where buttons. Okay. I know why you're saying that. It's because this is flux, magnetic flux. Not so. When you multiply times the number of turns, and because these are Webers, then that's why they are calling it Weber turns. Turns have no units. Yeah? They're just
Okay,
a
sir.
number. Yes, please.
Okay.
Kali, we can stop here.